I'm going to be talking about trigonometric identities. A trigonometric identity is an equation involving trigonometric expressions which holds for all values of every expression where they're defined. For example, we know that cosine squared theta plus sine squared of theta is equal to 1. Since this is true for every value of theta, this is a trigonometric identity. Another example would be tangent of theta is equal to sine theta over cosine theta. Even though this doesn't hold at theta is equal to pi over 2, where these expressions are not defined, it does hold for all other values of theta, that is, the values where they are defined. These kinds of trigonometric identities can be used to simplify expressions. Suppose that we wanted to know what 1 minus cosine squared theta divided by sine theta was. In this case, we know that cosine squared theta plus sine squared theta equals 1. So 1 minus cosine squared theta is just sine squared theta. Now if we divide this by sine theta, it'll simplify to sine theta. So using this identity, we're able to turn a more complicated expression into a much simpler one. An important skill to have here is to be able to verify whether any given trigonometric identity is actually true. Suppose we are given the identity tangent squared theta minus sine squared theta is equal to tangent squared theta times sine squared theta. To figure out whether this is true, we can start with one side of the expression and keep transforming it until it's the same as the other side. Alternatively, we could try to transform both sides separately until they're equal to the same thing. For this identity, let's try transforming just the left side. So tangent squared theta minus sine squared theta is really just equal to sine theta over cosine theta squared minus sine squared theta. Next, let's add these fractions under a common denominator. So here we have sine squared theta over cosine squared theta, and we're subtracting sine squared theta, but we want the denominator to be cosine squared theta, so we can multiply it by cosine theta and then divide it by cosine squared theta. And now we can combine these, and we get sine squared theta minus sine squared theta times cosine squared theta all over cosine squared theta. Next, on the top, we can factor out sine squared theta. We know that sine squared theta times 1 minus cosine squared theta is equal to sine squared theta minus sine squared theta times cosine squared theta by the distributive property. And then we divide this by cosine squared theta in the denominator. Next, recall that 1 minus cosine squared theta is actually just equal to sine squared theta, since cosine squared plus sine squared is 1. So this is sine squared theta times sine squared theta over cosine squared theta. Finally, we can separate out one of the sine squareds to get sine squared theta over cosine squared theta times sine squared theta, which is just equal to tangent squared theta times sine squared theta. When verifying trigonometric identities, it's often useful to put everything under a common denominator to make sure that everything is in terms of only sines and cosines so that it's simpler to deal with, and to use other trigonometric identities that we already know. Notice that we did all three of those things in this example.